Our first presentation today is by Jonathan Brandenburg, a survey of small satellite propulsion systems. So a warm round of welcome for him, please.
Good afternoon, and thank you very much. One of my roles here at AMSAT is the Assistant Vice President of Engineering. And as a part of that role, I do have the opportunity to work and manage the ASCENT program. And so it's my pleasure today to introduce a new ASCENT endeavor that I think will be very interesting to our membership and to our volunteers in engineering as well. So I am here today to talk about small satellite thrusters that are appropriate for CubeSats or what the industry considers small satellites. And I do need to remind us, I suspect, that our idea of a small satellite is sometimes different than the industry's idea of a small satellite. But it does range anywhere from your CubeSat footprint up to your, Volkswagen Beetle or even van size can occasionally be considered a small satellite. But what I'm talking about today are primarily the technologies that are applicable to the thrusting, the maneuvering, the orbital changes for true small satellites in our vernacular, being the CubeSats. And I'd like to talk a little bit about why, and certainly you can question these, but over the past several years, I would have to imagine that we've heard a lot about the requirement for deorbiting of satellites, the orbital debris problem, the pending and new FCC regulations around deorbiting your satellite. And in fact, I think we have seen in the news recently the first fine for an orbital debris violation. Correct me if I'm wrong, but I think that was Dish Network. Now, to be clear, this was not a substantive fine. This wasn't a backbreaking fine, but this was the test to show that the FCC could levy fines when they so desire for the violation of orbital debris rules. At least that's my interpretation of that relatively small dollar figure. But I also like to point out that, we kind of had a sense that debris mitigation was going to become an issue, become a factor in our satellites some years ago, and we've been working toward understanding how to deorbit on command. But what I'd like to point out is I'm also beginning to hear in conversations with organizations like Space Force and even the FCC, maybe some hints that the requirements will be evolving into the future as well. No rulemaking, no official on the record statements, but beginning discussions about how satellites will both have to report their own position accurately and not depend just upon ground-based radar to find them, but also the idea that we're going to have to be able to maneuver to avoid what we euphemistically call conjunction events, or and also at the same time to coordinate that maneuvering with a central authority. Now, to be clear, Space Force is very clear that they're not necessarily that authority. They're not trying to manage it, but they have mentioned to me the need to begin coordinating maneuvering events. And so this idea of small satellite thrusters is becoming increasingly applicable, I think, to our work looking forward. And that's part of what the ASCENT program here is to do, is to look forward at technologies and evolve new technologies for use in our future launches. So that's why I'm talking about it today. We have a GNSS program that we briefly discussed for flying on Golf T. We decided that was not mission critical for Golf T, and in fact may have been an additional technical burden on the staff, perhaps. But I wanted to at least continue that work, so we're spinning up an ASCENT-based GNSS evaluation for payloads on our satellites. Now, Golf T is going to be flying an ADCS, and I'm stealing a little thunder from our VP of Engineering, wherever he is sitting or he's probably writing the presentation right now, knowing Jerry. But we will be flying an ADCS on that from CubeSpace, at least at the current time. That's definitely the plan, and we've begun development toward that. But we really haven't had any sort of thruster opportunities. So I went and did a little research, and I went and had the opportunity to attend the Small Satellite Conference in Logan, Utah, where I saw a very cool product demonstration, so cool in fact that it looked to me as an opportunity for us to start, I guess getting excited is one way to look at it, but also beginning to think that it's truly something we can accomplish, and not in the distant future, but in the near future. We can accomplish maneuvering flight with our satellites going forward. But before I go into some of that, I'm going to take a brief moment to talk about the different kinds of technologies that we tend to see in small satellite thrusting. This was, after all, a talk that's supposed to be about a survey of small satellite thrusting technology, so let's go ahead and do that first. Some of us in this room have recently learned or relearned or already knew about the existence of this document called the State of the Art of Small Satellite Technology. This is a document that's published by the Small Satellite Virtual Institute. I'm missing an S because it's S3VI, I think. But a NASA-based institute to support the development of small satellites. On an annual basis, they release this report. And this is a long report that's listing dozens, hundreds of technologies that are applicable to small satellites, including CubeSats. And it ranges from attitude control systems to data processing systems to structures to communication systems and thrusters. So I shamelessly stole this slide from that report. And what I like about this is this nicely shows the categories of different kinds of technologies that are available for, quote, small satellites. You have your traditional solid motor, like your SRBs on the shuttle would be a big example of that, but certainly smaller solid motors are certainly plausible for small satellites. You have your traditional hydrazine, your hypergolic type fuels as well. And then more recently, especially in the hybrid and the mono biprop range, we've started to concern ourselves with so-called green propellants. And it's not because we completely are so worried about the environment, although we are in many cases, but we're more worried about the safety of personnel and the cost of handling those propellants. So a lot of these green propellants are green more because they're safe to handle, store, work on your satellite than anything else. There's also on the left side there your electrothermal and your cold warm gas. Those are basically your pressurized tanks of air that you just spurt out your nozzle. Sometimes you'll heat it up, but you won't heat it up to extreme temperatures. And then on the bottom right, you have your variety of electric thrusters, and I can talk more about those if there's questions, and I have time at the end. But as you can see from this graph, there's different groupings, and the vertical axis, the y-axis, so to speak, is really kind of the average or maximum thrust for that kind of technology. And being a logarithmic scale, I think that's the right term, you can see, of course, that solid rocket motors are extremely powerful. On the other hand, on the x-axis, the specific impulse, in layman's terms, because I'm actually a layman in this context, so I don't mind saying that, the specific impulse is basically the efficiency of the propellant based upon the weight of the system. It's just a really easy way to talk about it. And in many systems, that's based upon the exhaust velocity of whatever your propellant is going to be. So if you have an extremely fast propellant going out, which is often the case with electric thrusters, then you're going to have a very high specific impulse. So it's in a measure of efficiency is the way I'm going to describe it. And for the experts out there, I already apologize that I am simplifying it beyond the point of reason at some point. But there are several different kinds of electric thrusters. Your Hall effect are the ones that we've seen a lot of. I suspect that most of the NASA interplanetary missions that we've seen, even though I didn't do the research to say this, but from what I know, most of those are going to be Hall effect type thrusters. They're fairly large, they're fairly power hungry, but they're very reliable and they're very effective at what they've done. And they rely upon, well, Hall effect, the magnetic electric field is about my limit of knowledge on that one. But there's several others. Electrospray is another one that's interesting to me in the sense that it uses either a liquid or a solid propellant that it melts down real quickly, and using an electric field throws the exhaust out the nozzle. There's several different vendors for that, and it's a really affordable technology, and it's a moderately simple technology as well. But what I'm talking about today is the very bottom arc of that, which means in some ways the lowest thrust, but it has the benefit of being a very, very simple system, a very simple technology. And that's going to be the pulsed plasma or the vacuum arc. And what these will do is these will basically use an electric arc to ablate the fuel. ablate the material, which becomes the fuel. And so there's a variety of fuels that are used. You'll find some light metals, but oftentimes you'll find some high-tech plastics that are used as an ablative material. So it is my pleasure today to demonstrate such a plasma thruster here in this room. Before I go to that, though, I am going to at least slow down and pause and see if there's any questions that I can answer up to this point about the general concepts that I'm getting across today. So the question is, what is the material that's typically used with a vacuum arc? I haven't seen a typical material, but I think, and I'm pulling this from memory, so if I get the initials wrong, like a PTFE type material is one that I've seen is very common in that technology. But that's the only one that I found specifically referenced.
And then how long will that arc last?
How long will that arc last? Now, it doesn't provide a lot of thrust, but it can provide thrust for a relatively long time. And you're about to ask me a question I can't answer in a moment, so let me tee that up before I answer your question. The thruster nozzles that I have here today, which are air-safe thrusters, they fire in air, will typically fire easily 10 to 15,000 times. And when I say fire, let me set your expectations a little bit here. There's not going to be a 6-foot gout of flame spurting across the floor. It's going to be more of a pop, 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 or pew, 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 if you so prefer. So it will issue a lot of pews for a long period of time. And when we're working, of course, as you know, in a weightless environment, especially with a low mass spacecraft, that can actually yield a fairly substantial orbital change in orbit, such. As I repeat my word orbit again. All right, any other questions? Good ones. Hold on, we're going to have a wandering mic, Kip, so we're going to use the mic real quick here, if we may.
Is there something that burns or something that is consumed?
Is there something that burns or something that's consumed? I'm repeating your question anyway, even though you're on a mic. The answer is yes. It's not burning. That's actually key for most of these technologies. The only ones that are exothermic in nature are going to be your solid motor hybrid, mono biprop type things. But there is definitely a consumable in all these cases that I'm talking about today. In this case, it's that center core. And I will invite everybody to look at this once I get it sealed back up again. I'm happy to hand it around the room as long as you don't throw it on the floor or play catch with it or something. Does that answer your question, Kip?
Yeah,
How heavy?
is that consumable?
How heavy is the consumable? The consumable is actually fairly light. I don't know the answer to that. You're getting into those I don't know answers. But it moves very, very fast because of the plasma arc effect. Amir, yes, sir.
Yeah, doesn't any of this, I mean, don't we have to have like attitude control?
Don't we have to have attitude control?
Yeah,
yes.
to be able to use this at all.
Yes, we absolutely do, and I may have glossed over that a little bit, but in addition to the location information of a GNSS project, I briefly mentioned the ADCS on golf, but I didn't exactly make that connection, which says in order to use thrust, you have to be pointed in the right direction, which is where the ADCS does definitely come into play. You're absolutely right. I think Tom may have had a question back there. That was Tom's question. And I'm happy to take as much time as y'all will give me since I had 14 extra minutes, but I'm also happy to go on with the demo as well. So we'll go down that route. Oh, wait, we have one more. Go ahead, Lou. Mike's coming around to you.
My question was that the PTFE, is that making fluorine gas or anything toxic?
Does the PTFE fuel make a toxic gas? The answer is very plausibly in flight, but I don't have that problem. I don't remember what my fuel is, but it is actually non-toxic. That's part of the reason what I'm showing you today is actually not flight ready. Not only is it specially designed so it arcs in air and doesn't short out things, but the fuel and the housing is not space rated either. Alrighty, I will need the mic because I'm going to be moving over here. And how's my spacing and volume on mic? All right, good, good. As I noted to our AV engineer, Brad, I do have a tendency to yell in a group setting anyway, so he's also probably adjusting the volume. We'll deal with that. All right, so what I have here today is a development kit, and I want to say very specifically this is a development kit from a company out of South Africa called Hypernova Space. This is called the Lumen SDK, and the stated reason for Hypernova Space developing this is because they wanted people to begin experimenting with plasma arc technologies. This is an open source and open hardware-based platform. That's already true. It's licensed using a CERN license, which is something resembling a copyleft license. So you have to share your changes if it's going to go outside your organization. But he's even the company manager, Jonathan, who's brilliant. Jonathans are brilliant. Has mentioned that he's willing to host a seminar on how to develop our own nozzles and fuel systems. So he's very willing to share, presumably if we help advance the work. What else did I want to say? I think that's it. So we're going to go ahead and continue with a simple demo, and this will be going on the screen. Let me go ahead and show you what's up here before we shift it to the screen. We may end up switching back and forth. So I have here a very simple GUI that has been developed to control this from a development standpoint. And what we'll be seeing here is I'm going to be firing thruster number 1. You can see thruster number 1. This particular device has 4 thrusters, numbered 1 through 4. 1 and 2 are dummy loads. They basically dissipate as heat and flash a little bit of light when they fire. Thrusters 3 and 4 are actual spark gap thrusters that will ablate fuel, and they're the ones that make the more impressive pop-pop sound, if I'm easily impressed, I suppose. So what I like to do is I like to go ahead and first retrieve the telemetry, which you'll see when I come back to this screen, and then I'm going to fire the thruster 1 5 times, about 2.5 seconds apart. So with that, let's go ahead and switch camera over. Oh, I'm streaming? Can we put it on screen, or do we have that ability? We don't have the ability. Okay, that's fine. Watch for flashing lights here, if you can see it. So I'm going to go ahead at this point and power on the system, and apparently I forgot to open the port first, so let me start all over again. There we go. We're going to open up the port first this time. And then what I'm going to do is I'm going to go ahead and retrieve the telemetry. And what the developer told me that I should be doing here is making sure that the voltage is set properly for the power that we're driving through. And in this case, I'm not turned on. So if I power on, read the telemetry again, I'll see that my set voltage is 39.8 volts against a nominal commanded 40 volts. So my power systems appear to be working properly. The thruster is probably ready to fire. I'm going to go ahead and change this to a 10 count. I'm going to go ahead and change it to 500 milliseconds because otherwise 1 second between pops of light seems like an eternity. And when I fire, it's going to fire relatively quickly, and I need somebody to tell me if you are indeed seeing a light there. It's a dissipated light. So 1, 2, and 3. And we're seeing the flashing light. That is a simple dummy load. It just happens to flash a little bit of light while we're at it. Now what's interesting about this is if I go to the waveform, I actually see the telemetry captured during that run. And you'll see that our voltages reached as high as, say, 60 volts at peaks. And the current during those peaks was roughly 40 amps. So you can do the math and see for brief periods of time the amount of power that was dissipated by this system. It's got some internal capacitors that it charges up to store that. At some point, somebody's going to ask me today, what are the power requirements for this device? I sort of know the answer to that, and I'll show that to you proactively. So that's that. Now, what we also can do, and what I'll do this time, oh, we have a question. I'm sorry. Is that in microseconds? Oh, you mean on the waveform? That is in microseconds, yes. Thank you for asking. That is in microseconds on the x-axis. How efficient is this? You're going to hear me say a lot of times today, that is forward work, which means I don't know. But that's also part of the reason I'm standing here today is, again, we've got these SDKs. I bought 2 of them. Why buy one when you can buy 2, right? You know my motto. But what I want to do is I want to get this into our hands of our engineers, and I want to start researching and answering those types of questions. I've had one of our volunteers already volunteer to do some modeling of the thrust vectors and so forth. It'd be interesting to have somebody looking at it from an engineering standpoint as well. All right. What we can also do is we can also load pre-programmed systems. And I'm going to go ahead and load thrusters 1 and 2. What this will do is this, after a 5-second delay, which that part's weird, but patience. After 5 seconds, it'll kick off this program, and it'll flash both thrusters 1 and 2 10 times. And I hope it works. Okay, 5, 4, 3, 2, 1. Ha! The thing about live demos, you're always happy when they work. I'm glad they're working. So all I did was flash lights back and forth. Now you'll notice, by the way, this waveform was captured in this case, and it starts to actually clip a little bit on these thrusters. We're actually driving more power through than these sensors are capable of receiving. But when I change my firing sequence to fire 3 and 4, which is what I'll be doing now, this is where you're supposed to ooh and ah, because something very exciting happened in about 5 seconds. There you go. Pop, 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 pop. Now, I will put the cover back on this and hand it around, and what you will actually see is you will see burn marks in that center fuel rod for all the times that I fired this thruster, and that's what happened there. Not a lot of thrust, but continuing thrust for a long period of time will give us some ability to maneuver our satellites. And again, my objective here today is to show off something that I think was pretty darn exciting, an accessible SDK that we can get our hands on for developing electric thrusters. And at the same time, I wanted to make sure that we had the opportunity to engage our volunteers in that effort. So now here's we get to the point of I can't answer most of your questions. Yeah, go ahead, Bill.
Hang on just a second. There we go.
Is that voltage of up to, what, 60 volts or whatever it was, is that both the arc voltage that's vaporizing the material and the accelerating voltage, or is there another higher accelerating voltage to accelerate the plasma out?
Can you read the top of that slide for me?
It's a good thing to investigate, though.
Yeah, I'm honestly not sure about that. I just received this a very short time ago and haven't delved into it, but I would love to engage somebody, you, including the YouTube you, to join our team to begin investigating these capabilities, answering these questions. And to be clear, I'm not convinced this is the right technology even, or the right thruster for our use. But we won't know that until we start investigating it. So I want to start investigating it at this point.
Just a quick point of operation here. When you have a question, please raise your hand. Wait for me to bring the microphone over so our YouTube viewers can listen to it as well.
So given the current state of the technology, how much real estate would this take in a CubeSat? And how efficient, how much is that going to impact then your design of your CubeSat when you add this?
So Barry, I'm going to answer 2 questions, one that you asked and one that you didn't ask. The size of that, as you can tell, is about 3/4 of a U, and that is approximately the volume that would be required. I did promise to answer your power question, which I'll come up later. The question you didn't ask that I want to answer, though, was cost. Did I ever discuss cost? I talked to the manufacturer of this, and this SDK costs about $3,700, which is not a super scary sum. It's not something I'm buying out of my own budget, necessarily out of my pocket, but it's not scary for us to investigate. I'm told to expect that the flight model will be somewhere in the range of about $15,000 for a flight thruster, with 4 nozzles, so that's not too bad at all. Andrew, I believe you may have had a question.
Yes. Have you had time to quantify RFI, EMI, EMC concerns? Yeah. No, I'm just curious because, it looks like a spark gap transmitter.
It very likely is acting as a spark gap
Fundamentally.
transmitter, no doubt about that. I have
Yeah.
not characterized anything of that nature. I really have little technical information about the capabilities, like how much thrust even does this generate? That would be a very natural thing for us to have to answer. I'm looking forward to somebody answering that.
And a question about that question is, what type of delta in orbit could we actually expect?
And that the delta in orbit will depend entirely upon the mass of the satellite and the thrust available from that thruster.
Yeah.
I don't yet know enough to answer that.
Well, I'd just be very curious to see what this does to a linear transponder. Straight.
While firing, does it do
VHF,
anything
yeah.
fun?
Yeah,
There may be
yeah.
some challenges associated with that.
What a
Let me
noise
go ahead and
blanker
pull up
yeah.
one slide here. I'm going to go off mic for a second and not talk.
Did we have another question on the other side of the room? Nope.
Because at some point somebody would have asked me about power. Those are the power requirements for this particular SDK. The 12-volt line is the one driving the actual arc. So we're talking about 3 amps or more on 12 volts to drive the actual thruster itself. The rest are the power control, or the control electronics, and the CPU, I guess is what I'll call it. All right, great. I appreciate your participation. Any more questions before oh, Barry may have a question for me.
Okay. Simple question. SDK.
Thank you.
Small sat development kit, maybe?
Software development kit, but we tend to overload it a lot to mean any sort of development kit, to be honest. We can call it a system development kit, as Badale suggests. Lou has a question, I believe.
Are there any user hazards, like handling hazards, or
Are there any?
potential to get shocked or anything like that?
Yes, there are. I was specifically told not to put my hand or face within a foot of that when it's firing. There is a chance it could arc and ground through somebody, so we do have to be careful of that. I also removed the faceplate, and that's because if I'm ablating the air gap thruster into that faceplate, it doesn't hurt anything, but it'll eventually scar and obscure the faceplate so you can't see into the device anymore. That's why I take the cover off the front. So yes, there are definitely going to be safety considerations involved in using this. Did Will get the mic? Yes, Will.
Yeah. Has anyone considered using differential thrust for attitude control using something like this?
Has anybody considered using differential thrust? The answer is absolutely. I myself have been part of a team that has considered using FEEP thrusters, which is a form of electrospray thruster, to do differential attitude control. So I know it's possible. There's no specific reason that the nozzles have to be associated with the power electronics. Those nozzles are actually very removable. I told you I bought 2 kits. I did. I've already had to return one of the nozzles because it arrived to me non-functioning. I just pulled it out with a gloved hand just because I'm safe that way, put it in an envelope and sent it off. So it's very easy to replace these components. I've now been speaking for 30 minutes. I don't know how much time I really have, but if I have more questions, I'm happy to answer them.
You've got about 15 more minutes if you want it. Otherwise, you don't have to. Any other questions for our
Was there a
presenter?
question back there? Was that a question? Okay, no question. Well, in that case, thank you very much for allowing you to open today.